Everyone, welcome back to the problem solving session on diffusion in multi-component solids. So course ID is NOC 2417 and this is a week 5 for on the diffusion in multi-component solid problem solving sessions. And in this course, in this problem solving session, we will go over the topics that have been covered in this week 5, and afterwards second session will be the problems related to this week will be solved for this week. So first of all, so we will know about the, as I say, the first we will know about the topics covered in this week 5. So in this week, from lecture 20 to lecture 23 has been covered, which includes mainly based upon the solution for the diffusion equations in the different conditions. So we will go over from the lecture 20. First of all, in lecture 20, L20, the topic starts with the instantaneous planar source, solution to the diffusion equation and its application. So in this week, week 5, it mainly depends upon the solution for the diffusion equations. Solution for diffusion equation. In this, we will be solving instantaneous planar source. Instantaneous yes planar source. First, to solve any condition, whether it may be the instantaneous planar source or any other source, we will be considering fixed second. That is partial differentiation of concentration with respect to T to the partial differentiation concentration system. So D is the constant. Correct? Yes. For the instantaneous condition, instantaneous planar condition, instantaneous planar source, we need to consider a small block consider that as A, and we will be quoting element as P. This is considered as x equal to 0, and we will be considering the a small unit volume of this thickness delta. Okay, so this is the condition that we will be having. So it is the instantaneous planar source mainly used in the semiconductor industries, in which the doping of silicon is being carried out with the help of a diffusion process. A thin layer of silicon has been deposited on the substrate material. So we'll be analyzing the diffusion of silicon in this material. Let's start. First, I'll briefly explain the first what will be the uh, boundary. We assumes the thickness as a layer thickness of this layer as 0. Very thin layer, right? So that's why we consider as 0. And the boundary conditions for this one is x equal to the concentration of x comma 0 is equals to 0, so infinity comma t equal to, that is also equal to 0. This means that x comma 0 initial initially initial, that is t is equal to 0, there is no diffusion within this substrate material A. If you consider any x direction, any x position, the concentration of silicon is 0. That is, concentration of B element is 0. Second boundary condition is the element which is present here can't diffuse completely at the end. C is equal C, that is infinity comma 0 T. If you diffused it for, if you annealed it for T times, then also at the infinity it can't able to reach at the end. This is the meaning of this boundary conditions, and we will be considering the quantity of deposited per unit area is delta, that is given as 0 comma infinity c into dx equal to delta. So then if you consider this equation and applies the Laplace transform, so we will be getting infinity integration of 0 to infinity e raised to minus kt dou c into dou t into dt 0 comma infinity e raised to kt into dt. So considering only LHS, LHS 0 comma infinity e raised to kt into dou ct into dou t dt, integrating by part because it's exponential and here it is dou c by dou t. So we will be doing integration by part, that is we will be applying u comma v rule. U is equals to, I let exponential is at the end, so that's why e raised to minus kt and dv is equals to dou c into dou t into dt, right? So first we will be differentiating. Du is equals to minus k e to the power of t, v is equals to constant because it is differential. So by applying by part, that's integrating by parts, 0 to infinity e raised to kt into, dt. Then apply 0 x comma 0 plus k into c bar. So similarly, we will be considering RHS integration, that is equal to d 0 to infinity e raised to kt dou c square into dou x square into dt, d into, so we'll be taking inside this one 0 to infinity so this will be like x square e raised to kt into c into dt, right? So then we will be doing, so consider this one as initial condition, that is this one, for so we know the c, we are considering the steady state condition, so that's why d is equals to dou c bar divided by dx square. Then LHS is equal to RHS k into c bar d into dou square, and then finally we have this equation. And by solving this diffusion equation, so solving this diffusion equation, so I'll write one more time. C bar equal to delta root kd exponential of minus root k into d x. So this is Laplace inverse we have to apply. Delta divided by root kd exponential of x. So by solving this Laplace transform, we will be getting the concentration of x comma t. 1 minute, I will erase it little bit. 4 dt, right? So, so how this can be interpreted? We can take the ln on both sides. Take both sides. Ln c is equals to minus x square divided by 4 dt plus ln delta pi dt. Okay. So solving, so interpretation of this equation is, so taking ln on both sides, we will be getting plot of, yeah. So now I am getting a straight line correctly. This is the straight line that we will be getting, and we will be plotting we will be plotting ln c versus x square. The slope of this one will be minus 1 by 4 dt. So this will be the solution to the instantaneous planar source. And when we plot the c versus So it is mainly depends upon the diffusion itself. So here the L21 is based upon the solution for the diffusion equations for the semi-infinite slab and its application in the carbon C. Will be directly will be same. We'll be using the same. We'll be using fixed second law. Dou C into dou T. Sorry, D is constant. Dou X square. And so I will write the diagram here. I won't solve completely. I just write the initial condition, boundary conditions, and I will write the solution. So here it is CS, and here it is C naught. It's a surface concentration. So we'll be compressing from this side, x equal to 0 to x equal to infinity, and we'll be moving from left hand side to right hand side, x value. So initial condition, so x comma 0, that is C naught value. Yeah, that will be equal to 0, and here it is CS, and these both are boundary conditions. Zero. So this is, I will explain the boundary condition as well as the initial condition. Initial condition. What is the initial condition? That is T is equals to 0. This will be the T at T is equals to 0. This, the concentration at this surface or any other surfaces, that will be a 0 concentration of the carbon that we have. We are doing the carburizing. Right? So that's why the carbon concentration at T is equals to 0, that will be 0. The boundary condition says that at x equal to 0, at this boundary here, at any time T, the concentration of the carbon is Cs, and the carbon cannot reach to the other end. At x equal to 0, if you carburize it, this steel, you have to take a thickness of a steel in such a way that the carbon can't reach to the other side of the steel. This is the another condition. And similar way of instantaneous planar source. Instantaneous planar source, how we have solved the second law of diffusion by taking second law of diffusion. Similarly, we have to take this second law and we have to apply the Laplace transform, and then we have to get the solution for the diffusion, this carburizing diffusion equation. Yeah, the solution for this carburizing diffusion equation is C is equals to CS 1 minus error function x by 2 into root dt. So we'll be solving some of the equations from this one, and next is solution for the division equations for the binary division couple. Next condition is binary division couple. For that, we will be drawing a division couple. They are assembled. Its initial contacting plane, and this is the initial concentration C bar, and this is the initial concentration C plus, C minus, and C plus. This is x equal to 0 and x equal to minus infinity and x equal to plus infinity. Considering the same second law. So second law, that is tau is equal to d into log c square into tau x square. Similar initial conditions. X comma 0 infinity c plus 0 infinity. That means if you consider any x value from x equal to 0 to minus infinity, the concentration of this side will be the minus c minus, and from x equal to 0 to plus infinity, the concentration will be the c plus. And the boundary conditions are conditions is infinity c minus. Okay, this will be the these boundary conditions are very different from the other boundary conditions. So here we have considered the minus infinity at any time. The concentration towards this end will be the c bar always. If you diffuse for any time intervals, the concentration at the left hand will be c minus, and towards the right hand it will be c plus. And the solution for this diffusion equation, the general solution will be the c of x comma t minus c plus divided by c minus c plus 1 by 2 1 minus error function x by 2 into root dt. So this will be the solution for the binary conditions, binary diffusion couples. And last is solution for the multi-component diffusion equations. Solution to multi-component sorry, I will write it here completely. Multi-component diffusion. So previously we have considered only two elements. That is a binary equation. Here we will be considering the n number of alloys. N number of alloys. That is Ja bar equal to minus J equal to 1 to n minus 1 Okay, consider the fixed uncensored formalism IJ. So fixed second law applicable for the uncensored multi-component system, that is uncensored formalism. So in the video lecture demonstrated for the quaternary system, that is n equal to 4. First step is writing the flux equations, that is flux equations in the above mentioned conditions. J1 is equals to minus d tilde. So I will write it for the ternary system, that is n equal to 3. 3 1 1 dou c1 into dou x, 3 1 2 dou c2 into dou x. J2 equal to minus d into d3 2 1 dou c1 into dou x minus 2 2 dou c2 into dou x. Then apply the continuity equation. For this given condition, second step is continuity equation, dou ci into dou t tilde into dou. So just apply the whatever the j value that will be given written in the flux equation here. You just insert this equation. Then we will get a matrix of this thing. T tilde then apply for the similarity transformation matrix. Finding the eigenvalues and eigenvectors of D. Then finally we'll get the concentration of this multi-component system 1 by 2 into I P I into error function P minus P inverse C bar plus 1 by 2 I plus error function is P into P inverse C plus. So we can say here directly by solving this, by taking these equations and simulating in the MATLAB, we'll get the concentration profiles with respect to the so how this will be getting with respect to C versus X. So how we will be getting, if we have an experimental value, we can predict the concentration profiles. For binary, it will be same thing will be reduced to what we have derived with the previous condition. That is in binary condition, d equal to di and p equal to 1. So this is all about the this today's video series. Solution for the diffusion equations in a different conditions. That is, first semi-infinite, a planar source, instantaneous planar source. Second condition is semi-infinite slab and its application of carburizing, and you can do real-time examples and you can solve for those equations also. And second is solution for diffusion equation for the binary diffusion couples. Third is multi-component diffusion couples. So this can be used for high entropy alloys, superalloy diffusion, superalloy diffusion, or precipitate diffusion, analyzing the precipitate formations, and so on. So will be next we will be moving towards the problem solving sessions. Okay, first problem is from the Laplace transform. So this will be C. Okay, let's start with this equation itself. Match the following given in the list 1 as well as with respect to list 2. And here this in this equation, so solution for this will be given is given in the last, not this week video lectures. It is given in the fourth week video series. That is in a refreshment of Laplace transform. That is first, sir, the equation for the Laplace transform of cos pt is given as, we have already solved this equation as some constant s divided by s square plus pt. That means this will be, I will write the answer here. 2 in correct answer is 2. And sin pt, some constant, sorry, sin pt he has given, right? So p divided by s square plus p square, right? So where we are getting this one, p into s square into, that is, sorry, as 1, then sine hyperbolic of b into t, b divided by s square minus p square. Whereas for fourth, that is cos hyperbolic of b into t is given as, sorry, I have to write the answer here, right? Third one is fourth. Fourth one is third. Final. So this will be the answer for the given this problem. Next problem. Given, consider two hypothetical metal A and B after a 30 hours of a heat treatment at 100 degrees Celsius and subsequently cooling to a room temperature. The concentration of A in B is 3.8% at 10.7 position within the B metal. If another heat treatment of 30 hours, what will be the position of 3.2 weight percent of A? Sorry, it should be 3 weight percent. Concentration should be same. Uh, Assume that the pre-exponential and the activation energy for the diffusion coefficients are 1.8 into 10 to the power minus 5 and 1000, so 1,52,000 joules per mole respectively. He has given heat treatment time as 30 hours, temperature as 1000 degrees Celsius, and the concentration is same, and the x value 10.7 mm. So T1 is 1000, T2 is 800 degrees Celsius. So I will explain the first question, then we'll move to the solution. Consider the hypothetical diffusion couple A and B. So he will be doing some annealing of 30 hours. After that, at 1000 degrees Celsius. So after that, he will be finding this will be x equal to 0. Okay. So after that, at x equal to some distance, consider x equal to 10.7 mm. Okay. He is finding here the concentration is 3 weight percent of A. Here this is B side, but the concentration of A in the B side is 3 weight percent at this position, right? If you do the same heat treatment 30 hours, but he has changed to the 800 degrees Celsius. What will be the okay? So first, after 800 degrees Celsius, if you do the same heat treatment, if you analyze at same distance, that is x equal to 0 to x equal to 10.7. Sorry. Need to calculate this one only. little bit confusion. Okay, so need to calculate this x value where it will be determined when need to determine the x concentration as t. So what will be the distance from here? Okay, so let's solve this question. First, need to determine the d value at two different temperatures. First step. So basic equation is d equal to d naught into exponential of minus q by r into t. So at 1000 degrees Celsius, okay. So if you consider, he has given the q value also and t exponential term also, 1.8 into 10 to the power of minus 5 exponential of minus So 1,50,000 divided by R is 8.31 into T at degree Celsius. Need to add 273 to this one. Then 1273 need to convert into Kelvin. 1273 Kelvin. So this is the D value. Okay. So please do the calculation. This will be 2.146 into 10 to the power minus 15 meter square per per second. So similarly, need to calculate for the 800 in plus 273, that will be 1073 Kelvin. So D is equals to, so this will be the D1 value and this will be the D2 value. 1.8 into 10 to the power minus 5 exponential of minus 1400 divided by 8.31 into 10 to the power of 9, sorry, 1073. Then D2 value will be 2.071 into 10 to the power of minus 13 meters square per second. So this will be the D1 and D2 value. Then what we will be doing here is need to calculate the x value. So we will be using the generalized condition x by root dt is equals to constant. That means x1 by root d1 t1 equal to x2 root d2 into t2. As we know, t value is the same, the equation will be reduced to x1 by root d1, x2 by root d2. The x1 value will be, initially has given 10.5 mm, right, into 10 to the power of minus 3 root d1 value is 2.146 into 10 to the power of minus 15. We don't know the x2 value where it will be diffusing, and the d value here it is 2.071 into 10 to the power of minus 13. 1 minute. Yeah, sorry, this I think I got a mistake here, simple mistake. The diffusion value should be reversed because it's a common thing. Higher temperature should have the higher diffusivity value, that is 2.07 into 10 to the power minus 13, 2.146 into 10 to the power minus 15. So it's having lesser diffusivity value because of lower temperature. Need to reverse it also here. Here it is 2.07 into 10 to the power minus 13, 2.146 into 10 to the power minus 15, right? So by solving this one, the x2 value will be 1.6. Oh, sorry. So you will get some different value here. Please let me know the x value what you will get in the comment box. Okay. Yes. Let's move to the next question. So find the eigenvalues and the similarity transformation matrix P of the following interdiffusion matrix. Yes, you just do this one and we'll be discussing. Okay, first I have to write it here. It is into 10 to the power of minus 13 micrometer per second. 6. Okay, that will be. It's a first we need to determine the eigenvalues. We know the eigenvalue can be determined a into minus lambda I is equals to 0. Consider this one as A matrix. Lambda I is equals to 0. The A matrix is given as 3 minus 4 2 2 minus lambda identity matrix 1 0 0 1 to 0. So then 3 minus 4 2 2 lambda 0 0 lambda into 0. So then afterwards 3 minus lambda, that is minus 4 2 2 minus lambda. So need to determine the determinant of this one. 3 minus lambda into 2 minus lambda. So minus into minus, I will write here completely. 2 equal to 0. 3 minus lambda. So I will directly write the multiplication. It will be long. 3 into 2 6 11 3 lambda minus 2 lambda plus lambda square, and here it is 8. Okay, so quadratic equation will be minus lambda square. This will be minus 5 lambda, and this will be plus 14. The lambda value will be perfect square is given as 7 and 2. Solve this equation. Solve this quadratic equation, please. So here the solution for this quadratic equation will be in terms of the imaginary number, but need to get the division equations coefficients value should be in the positive values. So if you make this problem, 1 minute, if you consider here it is, to get the simplified equation to avoid the imaginary number, we'll consider this is positive 4, right? So here it is positive and here it is negative value, and finally we will get it as minus 2 value here. Let's write one more time. Hey, yep, this, yeah. So here it will be a negative value and here it will be a minus 2, and here the by doing minus b into plus or minus root p square minus 4ac divided by 2a, the lambda 1 and lambda 2 value will be, lambda 1 value will be, so it will be 5.372 and lambda 2 value will be minus 0.372, right? Yes. So these are the eigenvalues. Next, need to determine the transformation matrix P. That means eigenvectors. So considering the lambda 1, so I will write first A matrix. This is A matrix that we have. Yeah, here I have 3, 4, 2, 2, and lambda 1 value is 5.37, lambda 2 value is minus 0.37. So considering the, first of all, considering the lambda 1 value, this value, three minus 5.37, 4, 2, 2 minus 5.37. Okay. So this will be, solve this one, 1 minute. 3 minus 5.37. Here it will be minus 2.374. So determining the eigenvalues x1 and x2, that will be equal to 0, 2, 2 minus 5.37. It is again minus 3.37, x1 and x2, that will equal to 0. Multiply this with this row, so minus 2.37 x1 plus 4 into x2. If you consider x1 as 1, then x2 value is given as 4 by, sorry, x1 is 1, so 2.37 divided by 4.59. Again, if you consider the lambda 2 value, that is minus 0.37, 3 minus 0.37, 4, sorry, 2 plus 0.37 to x1 and x2 equal to 0. 3.37 to 4, 2.37 x1, x2, 0. 3.37 into x1 plus 4 into x2. So here we need to consider x2 as 1. If you consider x2 as 1, then the x1 value will be 4 by 3.37 minus 1.186, right? So eigen vector will be simple 1.59, 1.186, 1. This will be the your transformation matrix as eigenvalues. Next problem is consider the hypothetical diffusion couple A and B. So obtain the diffusion depth of 300 micron after the diffusion annealing of at 1000 degrees Celsius for 20 hours. Same diffusion couple annealed for 40 hours. So what will be the expected diffusion depth? So if the diffusion coefficient increases by twice, then the diffusion depth will be, so what will be the diffusion depth? So in this question, we will be understanding the effect of diffusion annealing as well as the effect of diffusion coefficient value by considering the equation x by root d into t equal to constant. So try to solve this one right now. Okay, so first we'll be solving at the same division couple and for different time, that is 40 hours. So what will be the division depth? The x bar, we will be using x1 by root d1 t1 equal to x2 root d2 t2. In case 1, we are not changing the division coefficient value, we just changing the parameter of time t. Okay, in this case we are keeping the d value as constant, so that's why this equation reduced to x1 by root t1 x2 by root t2. Then x value, x1 value is 300 micron and t value is given as 20 hours. We'll keep it in hours only. So x2 value need to determine, need to calculate at 400 hours. Solving this equation, t 300 so after annealing at 40 hours, we will be getting 424.26 microns as a diffusion depth. See, if you increase the diffusion annealing time by keeping the temperature as constant, so you will get the more diffusion depth. It's not directly that if you increases the double the time, you will get a 600 microns. So it is varying exponentially with the root exponential. That's why parabolic kind of thing. So that's why it should be 4.24. You should to keep in mind. And this type of questions are commonly asked in the gate exams as well as in the final exams of this course. Next is, if we increase the diffusion coefficient values twice, so what will be the diffusion depth? White screen. Okay, so I'll write the equation one more time. X by root dt is equals to constant x1 by root d1 t1 equal to x2 by root d2 t2. So he has given, uh, but we are keeping the temperature as time as constant, that is 20 hours only, and temperature as 1000 degrees Celsius. So if the diffusivity value is increased, it's a hypothetical diffusion couple. x1 is 300, consider as d value. D2 value is 2 times of D1, so that's why it is D. Need to determine the x2, 2 times of D value. So this D value is cancelled and this is cancelled. 300 into root 2 to x2. X2 is 300 into root 2. Same. 424.26 micrometer is the diffusion depth. This is the diffusion depth obtained if we increases the diffusivity value. So this is all about today's problem solving sessions. So if you have any queries or problems, please let me know. Thank you for attending this session, and we'll meet in the upcoming sessions.